Hello everyone, and welcome to today's webinar, Tolerance as a Form. My name is Callie Schwartzley, Marketing Manager for ECM, and I will be your moderator for today. In addition to being a metrology services provider, we also take great pride in educating our peers in the field of metrology. We offer several training courses here at ECM, and we thought this would be a really great way to give you a glimpse of what you could be learning to advance your professional career. This is the first webinar in our educational webinar series, and our webinars will all revolve around educating you, the user of metrology instruments, and helping you to advance your metrology skill set. We appreciate you taking the time out of your busy schedules to join us today, and that is why we are keeping this webinar to a short 30 minutes of presentation and 10 minutes of Q&A. We will be keeping everyone muted throughout the presentation to minimize background noises. But please feel free to ask any questions you may have by using the question box on your control panel, and we will answer as many questions as possible at the conclusion of the webinar. Now, I would like to introduce today's presenter, our Principal Engineer and Lead Training Instructor for ECM, Tom Kinnare.
Thanks, Callie. Hello, everyone, and welcome to the inaugural episode of our, hopefully, webinar series. This is just the first of hopefully many. First, just a little bit about the company. I'll try to keep this real short so we can get to the meat of the subject matter today. We do a lot more than measure here at East Coast Metrology. We design and build test fixtures. We program CMMs. We do calibration and repair, calibration of arms, trackers, theodolites, and we also do some repair on theodolites. We do training and certification, some system integration work, automation work, alignments of all sorts. In the medical business, a lot for proton therapy, but we also do alignments for the power industry, and we do reverse engineering and design. We offer a variety of training courses. We can do them here at our offices or at your facility. Dimensional measurement training levels 1 and 2 is actually a course written by NPL. That's the British equivalent of NIST. Really good, basic, solid, philosophical courses about measurement. We do 2 levels of GD&T training. For most technical people, you jump right in at the intermediate level. We do equipment-based training with portable measurement, coordinate measurement systems. Mostly arms and trackers. We run the CMS certification course for the level 1 test, and we do some software-specific training: spatial analyzer, Faro, Cam 2, in 3 different flavors: Measure 4, Measure 10, or Measure X, and yeah, laser care and maintenance. Okay, on to the real subject matter. By the end of the webinar, you hopefully will be able to describe the shape of the flatness, straightness, circularity, and cylindricity tolerance zones and the relationships to datums. Quick hint, they shouldn't have any relationships to datums. They are called out independently of datums. Hopefully you'll understand that the reported value, that the value we report can be defined analogously to the design tolerance. Hopefully you understand the difference between deviations of a least squares best fit and a correctly defined report value. And hopefully you'll be able to describe how uncertainty can affect your pass-fail criteria. Okay, why form? Why choose tolerance as a form for the first webinar? It illustrates many aspects of GD&T inspection when you're using coordinate measurement equipment, and it does that without a lot of extra baggage and considerations, datums and material conditions. So we can really just focus on the tolerance zones and measurement. Another aspect of why form. Why do these tolerances exist? What are they used for? A lot of times they're used for sliding or sealing surfaces. Straightness and flatness, roundness, they all kind of control smoothness to a certain extent, not on the surface texture level, but on a gross macroscopic level. Important for sliding and sealing surfaces. Parts that mate by insertion. You'd like round parts to be round. so that when you put one inside the other, an oval part, might not fit if it's a tight mate. Controlling orientation of mating parts. If there's a big bow in a surface that another part mates to, that mating part may be pointed up or down slightly compared to the kind of average surface, and that may not be what the designer wanted. Optical properties. If you're making mirrors, you may want that to be dead flat or have some other shape, and a whole host of other reasons. Specifications. GD&T is controlled in the United States by ASME Y14.5, 2009 edition. ISO breaks the subject matter up into dozens of individual specs, and I don't know them all. Functionally, ISO uses pretty much the same symbology that we use for the ASME spec, and the meanings are pretty close to the same. There are some fine differences, but in general, you'll be safe if you kind of interpret a drawing that references the ISO spec. If you interpret it just like 14.5, reasonably safe. A couple other good documents and specifications. Y14.5.1, that's 1994, is a mathematical definitions of GD&T. Really good for people who can do vector math, but there's also some good material in there that may help explain what they were really wanted, what they were really getting at when they wrote the 14.5 spec. Y14.43, gauges and fixturing for GD&T. I find this one really useful, particularly for thinking about datuming. It explains how to build gauges, taking into account various callouts you might have on a drawing that you're building a gauge for. ASME Y14.45, the GD&T reporting spec. That's not out yet. I'm actually on the committee that's trying to write that, and we hope to have that out in time for the spring ASME meeting. It's going to be close. It may be sometime later in 2017, but unless something goes terribly wrong, I'm almost certain that that spec will be out this year. Third-party books and sources. There's tons of books out there on GD&T, many books, and if you go looking for them and read reviews, you will find people like and don't like certain books. Sometimes when they say this book was terrible, they'll reference a book that they really liked. I think what it comes down to is just that different people have different learning styles. If you buy a book and you don't like the first one you get, try another one. You'll find something that is understandable and kind of dovetails with your philosophy. Company standards also can sometimes control GD&T. They may have particular uses they want a designer to use, for instance. Okay, tolerances of form. There are 4 tolerances of form, and we see them here accompanied by their symbols: straightness, flatness, circularity, and cylindricity. The symbols look kind of like what they represent. The straightness symbol, just a straight horizontal line. Flatness looks kind of like a square plane in an isometric view. Circularity, nice circle. And cylindricity looks like maybe a shaft being rolled between 2 planes. And and that kind of similarity between what you're trying to control and call out and the image is carried through most of the symbology used. Another note: profile can be used to control shape, but there's a lot more that goes into profile, including referencing datums. We'll talk about that hopefully in a future webinar. Okay, all tolerances of form control shape by establishing an acceptable envelope of deviation, and they're applied without reference to datums. You're just checking the shape to itself. This makes them particularly well suited for the CMM because we tend to measure a bunch of points and then best fit, and that best fit is allowed to, you can allow it to move in any direction, which, fine finds your measured value without reference to any particular datum. You kind of date them to the feature itself. And all tolerances of form apply over the entire extent of the feature they're called out for, unless they're bounded in some way. So hopefully for the designers out there, hopefully you'll never write a tolerance of form with a datum attached, as shown in the right-hand view. And most of the CAD software out there is smart enough to know now that if you're tolerancing form, it's not even going to let you put a datum in. Okay, by definition, the tolerance zone for straightness lies between two parallel lines in the plane of the view, and this is a direct quote now, where the elements to be controlled are represented by a straight line. So for this, I have a bar here with a chamfer on the edge, with the straightness call out along the top edge. And the straightness applies to each element across the entire surface in question. Sorry. An element is kind of like a cross-sectional cut. And in the case of a rectangular bar, you'd have a number of lines running down parallel to that front face. Old school, you would take a dial test indicator and run it down the part, look for the minimum and the maximum deviation, and that's what you would record as your straightness. Similarly, for a cylindrical piece, you know, you'd have an element on the top. Since it applies across the entire surface, you'd have to rotate it, and you know, you'd end up with multiple elements down the length of the piece. You know, how many elements are in a surface? There's an infinite number. They could be as close together as you could possibly take them. And part of the art of measurement is, you know, determining how many are good enough, how many you need to be representative of the part. Okay, kind of zooming in. We've got our straightness tolerance at 5 thousandths. The tolerance zone, two lines bounded by 5 thousandths. Those lines could tip up or down as you move from left to right. And the only requirement is that the actual surface, you know, falls within those two zones. Straightness can be applied on a per unit basis. So in this image, whereas the callout on the right would apply over the entire feature, this callout per unit length, which is shown by having the slash and then the unit of length on the right-hand side of the slash, it kind of replaces a note. Part must be straight within 5 thousandths of an inch per every 1.2 inches of length. All right, what this works out to is you'd subdivide the surface. And every 1.2 inches, you would look at the straightness of each individual segment. Unfortunately, you know, that could be divided any number of ways. And per the spec, you have to look for any segment 1.2 inches long that, you know, deviates the 5 thousandths of an inch in order to make sure that a part's conforming. Software can help quite a bit. You know, otherwise you'd have to do like a running total of every 3 points you measure. Okay, composite tolerancing. So sometimes you can combine feature and a unit-based callout as a composite tolerance. In this tolerance here, there's just a single tolerance box, regular tolerance on top, a unit-based tolerance on the bottom. This would mean just about the same thing as the previous slide. Call it in the previous slide. Bounding. A lot of times, well, not a lot, sometimes you'll see this double-headed arrow, an S and a T or some other letters underneath. Someplace else in the drawing, points S and T will be called out. Typically they'll have basic dimensions that control their position. Sometimes they'll be, you know, right on the corner of a feature or some other easily identifiable point, and that'll mark the boundary over which you're worried about this particular tolerance, straightness in this case. Moving on to flatness. The tolerance zone for flatness lies between two parallel planes separated by the tolerance. So for this callout, we'd have a 100 thousandths thick tolerance zone. It would lie over the entire extent of the feature. This is our controlled surface. Zooming in, we have our zone, and the actual part, with its variations, in order to conform, its highest point would have to hit that, and then the lowest point would have to be within the bottom tolerance. Again, that tolerance zone is free to move up and down to hit the highest or lowest point. Once you've touched off on one side or the other, it needs to stop. And it's even allowed to pitch and roll and rotate in order to encompass the surface, but the entire surface has to lie within that box after you're done. In some ways, you can think about straightness, flatness as straightness, but with elements running in all directions. Longitude for this flatness callout longitudinally, or across the piece, and even diagonally. Flatness can be applied, on a per unit basis, but for flatness, the unit is an area. And that area could be either circular or square patches. Again, you've got the slash and your basic area over which you're going to compare. In this case, it would be a circular area with the diameter symbol, 1 inch in diameter. Over here, I would have a square, 1 inch per side. Okay. Looking at it again, so I'd have to consider every circular area 1 inch in diameter all over the face of the part and search for a 10th out deviation in any of those. The same with if I had a square, I'd have to be able to pick any square and have it pass that 10th out criteria. One way to shortcut it, if the part is good and over the entire extent of the part it meets that spec, you don't have to try to break it up into small areas, because if the entire surface meets that spec, naturally any subsection of that surface would also meet the spec. Typically, if you're talking about flatness and you're talking about just measuring a particular area, designers will show that with crosshatch on the face of the drawing. So considering our hexagonal block, they might just draw a cross-section area like this. Sometimes you'd have basic dimensions controlling the area. Sometimes it would just be tagged to easily identifiable features on the part, in this case these 4 corners. And the callout will have some sort of note saying that the tolerance only applies in that area. Circularity. Circularity, the tolerance zone is defined by 2 concentric circles. They're separated radially by the tolerance. That's not the difference in their diameters, it's the radial difference between them. So my outer diameter would be 2 thou larger than my inner diameter in this case. Right? And you're looking at elements again. For circularity, the elements are perpendicular to the center line, so you get nice round sections along the length. Cylindricity, the tolerance zone lies between 2 concentric cylinders that are separated radially by the tolerance value. Right, so you end up with these concentric cylinders, a green zone, and the entire surface of the gray part must lie between those. And it's kind of like a simultaneous circularity and straightness. Right, for a cylindrical part, circularity would not control, say, the part coning very well. It doesn't even control bow on the part, because you're looking at the local center line at each element. So, yeah, cylindricity is really what you need to control a cylinder. Okay, So that's just a quick look at the different tolerance zones for form. Now we'll talk a little bit about measuring flatness. It looks like I'm dragging a little. I may run just a little over, but I'll try to catch it up. So here we have a sample call out. We'll use this example throughout the rest of the measuring section. We've got this bar, 8.78 long, half an inch thick, plus or minus 10 thou, with a flatness of 5 thou called out on the top surface. You know, approaching any measurement job, the first thing you need to do is plan your measurement. You know, there's a whole host of factors I'm not going to talk about. Just a real quick note about number and distribution of measurements. And technique can affect that. For instance, in this right-hand picture, you know, if I was using the dial test indicator, I'd be taking stripes down the part and across the part. Over here, if I'm looking at planning measurement for a CMM or a drop indicator or height gauge, you know, I'm going to have individual points. An even distribution is usually best. You know, for instance, if I crowded a bunch of points down at one end, you know, these points, and then, you know, I best fit through there. These points here may have an unusually large looking deviation. You know, trying to distribute your measurements evenly will kind of head that kind of bias off. There's no hard and fast rule for the number of points. You know, obviously you want to take enough points to accurately characterize the part. You don't want to take so many points that it takes you 3 weeks to measure flatness. So the number of points you take is going to depend on your tolerance, the size, and the part quality. If you've got a really good part to begin with, you can probably take fewer parts. If you've got a part that is a problem, looks bad, you're probably going to have to take more points to accurately characterize it. Measuring conventionally on a tabletop with, say, a dial test indicator, a drop indicator, or a height gauge, setup becomes really important in this kind of application. You know, the instruments typically are referencing 0 from the granite tabletop as a datum plane, and if there's a long bow to the part, you're not set up parallel, then you can see a significantly higher deviation from one end to the other than you would if the part was more nearly parallel to that basic table. You know, one good way to do that would be to support the part just on 3 points. Points should be well spread across the part, maybe 2 at one end and 1 on the far end, near the center, to kind of level the part out before you begin measuring. Setup's less important measuring with a CMM because most software will be able to find a best fit plane and they'll use that as a reference plane for measurements. And so here we have our part. It's not well oriented, but the software calculates a nice best fit plane that we can use to accurately characterize the part. Now, one thing that may have just a minor effect, it might be enough to just throw you well, let me go back. Okay, most software uses the least squares best fit. Right, that minimizes the sum of the squares of the deviations. Right, and then we look at the maximum and minimum deviation from that least squares best fit plane, and we take the difference between them and we declare that to be the flatness. But GD&T wants the deviations, not the square of the deviations, but just the deviations minimized to determine the measured value of flatness. If you've got a really good part, the difference between minimizing the squares and minimizing the deviations is really small and almost negligible. If the part's not so good, you may be able to manually adjust the angle of that plane to get a slightly better answer. And new software GD&T functions are getting better and better at doing this. Spatial Analyzer is one company I've talked to about this quite a bit. You know, and their basic methodology is to solve a least squares best fit plane, and then the software has some sort of algorithm for tipping that plane and finding a slightly better, slightly smaller flatness value. Okay, reporting. Okay, Y14.5.1 is the document, that's the mathematical definitions document. That's what actually describes or defines the defines the actual or measured value of flatness. And it just defines it as the smallest flatness tolerance to which the surface will conform. Similarly for straightness, circularity, and cylindricity, the wording is the smallest tolerance of whichever type to which the feature will conform. Right? And that definition, almost makes us have to go find that smallest value. And in a tabletop setup, that might mean zeroing on a couple different points, and then taking our measurements again. In the case of CMM measurements, it might mean actually having to manually tip the plane or using the GD&T software to do that for us. Oh, one thing about using software, I really recommend that you test it. The software gets better all the time, but in the early days of GD&T, I used to take and I would feed sample point sets to it, to different software, and sometimes I was appalled by the results. Like I said, they've gotten much better over the years, but I highly recommend testing so that you know exactly what you're getting. Okay, where did I get off track? Okay, and we search for the smallest value by reorienting the tolerance zone. Yeah. Now, Y14.45 is a little more practical, and again, that's that brand new spec, hopefully coming out this year, about reporting on GD&T. It defines 3 different levels of reporting. Type A, pass-fail. Type B is a single number which would describe the worst case, and depending on the tolerance, the type of tolerance that's called out, that can be an interesting process. Profile the process is really complicated. Yeah, to get that single number. Performance not bad, and what we do most of the time in terms of taking a best fit feature and then looking for the maximum deviation is perfectly adequate. Type C, again, uses that single type B number, but then supplemented by additional data. And of course, in the CMM world, whether we're portable CMMs or stationary CMMs, we've been doing that for a long time with whisker plots and color plots of deviations for features. Okay, uncertainty. Y14.45 notes that uncertainty should be considered when deciding if a feature meets its GD&T tolerance, but it doesn't tell you how to do that. Just that you should consider it. ISO has a spec which requires you to subtract your uncertainty from the tolerance band. So if I had an instrument, well, it's most easily talked about, say, in terms of length. If I had a 5-inch bar, plus or minus 10 thousandths, I'm measuring it with a pair of calipers which maybe have an uncertainty of 1,000th. I would have to subtract the 1,000th from the 5. I can only say the part passed if I was within plus or minus 4 thousandths. This can make it hard, especially if you're doing tight tolerance parts, at around 1 or 2 thousandths tolerance or less. And I've heard rumors that ASME is considering a similar spec. And if anyone knows it for sure about that, I'd appreciate it if they would chip in with a comment on the screen, because that's going to be important for a lot of people. All right. So measurement uncertainty is difficult to ascertain with these kinds of measurements, particularly with the portable CMM equipment, like arms and trackers. Your uncertainty starts with the uncertainty of the instrument, and that may vary over the measurement envelope. Environment and operator can have a large effect. It can vary over time if your environment changes. And that's just for determining the uncertainty of individual points, right? Then we combine the point measurements to create average best fit features. The statistics are too complicated for me, right? The key thing is use good measurement practice, try to estimate your uncertainties, and then you can be prepared to defend close pass-fail calls. That's the end of the formal part of the presentation. I'd be happy to do questions and answers now. I thank you for your attention and hope that it was worthwhile enough that you'll come back for another one.
Thanks so much, Tom. I have a handful of questions at this point, but I do invite everyone, if you do have questions, now's the time to type them into your questions box so that we can go ahead and address those, or as many as possible. I will start with the first question, Tom. How can we control the roundness of spheres?
Oh, yeah, that's a good question. So for spheres, the circularity tolerance zone, the circularity tolerance can be used to control the roundness of spheres, and that's defined as two spheres separated by, the distance in the tolerance. Again, depending on the technique you're using, CMM, you could probably best fit, look for min-max deviations. If you're using tabletop equipment, you're probably going to be considering elements, right? Every element will be circular. Various cross sections through the piece.
Okay. Next question. Can circularity or cylindricity be applied on a per unit basis?
Okay. Yeah, so Y14.5 is silent on that issue. It doesn't say you can't, but unlike flatness and straightness, it doesn't have a section where it says that you can. For circularity, I have a little trouble imagining a case where you would be applying it on a per unit basis. That seems a little weird. For cylindricity, I could see someone trying to call cylindricity out per unit length. And, I'm not quite sure if that's proper because the spec, again, doesn't give us guidance. But you might be better served by having a circularity call out and a straightness call out on the piece independently. And then you could make that straightness call out per unit length.
Okay. Next question. What's the difference between cylindricity and coaxiality?
I think there shouldn't be a relationship between those two. I think maybe the question was really concentricity and coaxiality, which is a little off topic, but I'll go ahead and try to address that. So the usage is about the same. In GD&T, true position is used to control coaxiality, and concentricity does kind of the same thing. One key difference between them, though, is concentricity specifies how you're going to measure the piece by virtue of its definition. Concentricity talks about taking opposite points, finding the median point between them, right? And then looking at where that median point falls with respect to a cylindrical tolerance zone. If the part has maybe 3 or 5-fold rotational geometry, then you'd be taking points on those 3 or 5 lobes, and you would be finding the mean point of those. So concentricity is more complicated to measure. For the machinist, it means practically the same thing in most cases, but in terms of measurement, it is a lot more difficult and time-consuming for the inspector. And a lot of times, I see concentricity overused on drawings. They could call out coaxiality and be just as well served. The big time where someone would want to use concentricity is if they're trying to balance a part in a rotating application.
Okay. Next question. What is the ISO spec that requires you to subtract the uncertainty level?
Yeah, I'm not sure. I wish I could give you a number. I was talking it over with one of my friends at NIST, and the subject came up. And I just remember him, informing me of that. I can't give you a reference number for that. Sorry.
Okay. Let's see. Next question. When does Y14.45 become effective?
Okay. Well, 14.45 will be effective. I would imagine as soon as we can release it. Hopefully in time for the spring meeting, but time's starting to get close. Time's starting to get short, and I think we're going to end up being later than that. Even once that spec is put out, it's really up to the customer or your company to decide whether or not they want to adopt it. So even though the spec is released, doesn't necessarily mean that you have to conform to it. The big point is it will provide kind of a common language about reporting for people who are trying to requisition measurement services, so that they can communicate with the people actually doing the measurements, so that it's easier to provide them with what they actually want.
Okay. Do you have a personal recommendation for third-party resources for learning GD&T metrology operations that help prepare individuals for a training course?
Oh, that's a good question. I really like Bill Tandler's book, The Little Encyclopedia of GD&T. And that's available over the web. Bill has his own website. The book is comparatively cheap. It's small. It's not exhaustive. It doesn't cover everything, but it covers what you see in most practical work. And I really like the way Bill discusses the features. One of the guys here at the office has David Punchakar's book. I think it's Punchacar. And I've looked through that. That seems to be a pretty good discussion as well. And again, it's one of the less expensive ones.
Great, and to add to that, I actually have an attendee said that they have a great, fantastic material. It's called Techies for anyone who's also looking for another option. Is there a way to determine uncertainty for a measurement?
Yeah, well, okay, so it's easier where you've got a kind of a single instrument and single measurement you're trying to make, like if you're using micrometers or calipers, or a height gauge, something of that nature. When we start to get into the CMM realm, particularly single point measurements. How do I want to say this? All right. If you look at manufacturer specs, most manufacturer specs will not give you an uncertainty per se. They will give you a maximum permissible error. So you're not doing the same kind of basic repeatability tests that you would to develop uncertainty with a conventional length measuring instrument, say. We end up using the maximum permissible error in the same way as we would a statistical number. But that only applies to single point measurements. So, that's easy to say. Again, when you try to you take a point group and you best fit a feature to it, I don't know of any way to say what your uncertainty is going to be. There's probably statistical methods that would handle it. That's just, more than I know.
Okay, thanks, Tom. I do have a couple of questions. I want the attendees to know that I did get them, but I feel more comfortable having Tom answer those for you offline just because of their technical and specific nature. So I'll go ahead and have Tom contact you directly with the answers to those questions at the conclusion of the webinar. I wanted to thank you, Tom, for being our presenter today. And if you could just go ahead and move to the last slide of our presentation for everyone to reference. Thank you. If there was a question we did not get to, or if you have any additional questions, please feel free to contact training@eastcoastmetrology.com, and we can answer any questions you may have offline, like I mentioned. I want to thank everyone again for joining us today, and I hope you are leaving this webinar with some useful information. Remember that we've only just scratched the surface on this topic during today's webinar, and I do invite you to check out our website, eastcoastmetrology.com, for the opportunity to take one of our 2 to 3 day training classes at our facility or yours. We are always taking comments as to what you want to learn for our next webinar. So please take a minute to fill out our short survey as you exit, and we can have your feedback. Thanks again, and I hope you join us next time.
Thank you.